All right, let's get started. Welcome to the past seminar series. My name is Scott Moore. I'm the faculty director of PAT. I see some familiar faces and some new faces. For those that have come before and for those that haven't come before, all welcome. Please feel invited, welcome to come to future seminars. Today, it's a distinct honor to welcome Dr. Hanna Krasowski. Actually a name, Krasowski, that you will know from nonlinear systems and stability theorems. Anyways, Dr. Krasowski is a postdoc with Murat Arcek, also co-advised with Sanjit Seshia, actually two faculty members affiliated with PATH. And I'm reading right here from your bio on the webpage. So you got your PhD at TU Munich, advised by Matthias Althoff. And it looks like during that period was a visiting student at Caltech. So you've been in California before, with Aaron Ames, who is a robotics guy, really. Actually very famous for using control the Lyapunov functions for safety.
Yeah, the control barrier functions.
Yeah, sorry, control barrier functions, thank you. And master's degree at TU Munich, master's degree from TU Darmstadt. What's your hometown?
Ulm. So it's right in between Stuttgart and Munich. That's where I grew up.
Well, welcome. So expert in reinforcement learning, motion planning. I see on your website you describe autonomous driving and also maritime vessels, which is interesting.
So we will have one example from maritime vessels today as well. So, yep. So thank you for the nice introduction. Welcome everyone to my talk. I will talk about Provably safe reinforcement learning for autonomous vehicles, and that includes road vehicles and other vehicles like vessels. So let's dive into it. I think maybe many of you already had the pleasure to ride on a Waymo, but also maybe you learned about some discoveries from our planets due to space exploration. You know that drone delivery, especially to remote areas, is getting more often business case, and also in healthcare we have more and more autonomous systems that are interacting with our physical world and especially humans. So these are all very interesting and challenging applications for autonomous systems, and I want to briefly illustrate for you why this is the case. So often in autonomous vehicles, one task they have to do is plan a path, plan a motion, control themselves to a new location, to a new joint configuration for a robotic manipulator. And let's start with this example where we have some autonomous system here, vehicle, that tries to reach some other state in your state space, the goal area, with some paths. But usually we don't have one isolated world where we just have this autonomous system. We also have static obstacles that we need to detect and avoid. We also, in many real-world applications, have dynamic obstacles. And these are particularly challenging because we also have uncertainty. We cannot detect the world with absolute precision. So for static obstacles, we might still have reasonable noise, while for dynamic obstacles, main challenge is how to predict this noise will basically accumulate over time, and we will get more uncertain predictions with a longer time horizon. And obviously our own state we usually can also not perfectly observe. Now, this is already a very complex setting, but then sometimes you also want your autonomous vehicle or system not only to avoid collision and reach a goal, but you also want it to adhere to more complex specifications like traffic rules. So especially for autonomous driving, we not only want to reach a goal without colliding, but we also need to stick to red lights, we need to stick to stop signs. And this is actually the case for other autonomous vehicles application as well, where traffic rules is one example where we have a fairly formalized way of how this is already structured. And for, let's say, mobile robots in warehouses, we can basically come up with our own rules, more or less. Okay, so this is the problem we will look into today. And there are two solving paradigms with which we can approach them. One is reinforcement learning, which is especially in this model-free version, a method that is very scalable to high-dimensional systems that also can solve complex tasks like autonomous driving. We've seen that in the literature. But at the same time, this method is based on exploration, and because we usually don't know the outcomes of our next step, that is also often including unsafe exploration. And due to the fact that these networks in the end are usually neural networks, we don't really get an interpretability on their decision, maybe on our training and test set, but we don't really know how they will behave beyond this in the wild. So another way to approach this is a formal or like more controls perspective that is much more model-based, where you, for example, have a specification and a model, and then you use something like synthesis or model checking to either verify that your model already fulfills the specification or to actually obtain a provably correct controller. So with this, we actually get guarantees for our systems, and we also kind of formalize the specifications and therefore also the assumptions and the guarantees that we want to give. At the same time, these methods often don't scale as well to high-dimensional systems, and especially with dynamic obstacles, we often cannot globally verify a system because for autonomous driving, there can be infinitely many traffic situations that can occur. And another issue is that this model often is an over-approximative model. And if we have a simple model like a linear model, then we still have very efficient algorithms. But on the other hand, we usually also have much more over-approximation than a more realistic model would have. But more complicated, nonlinear hybrid models are much more difficult for these methods, especially if we need them in an efficient way. So I propose to find ways to connect these both paradigms, and by that hopefully get scalable and efficient algorithms that also provide guarantees. And the subfield we're looking into here today is provably safe reinforcement learning, which means that we saw the reinforcement learning process on the slide before. So in a standard way, we have an environment with a state so the state informs the agent about the state of the environment. The agent makes a decision, which is an action. Then the action goes into the environment changes and informs the agent with like how well this action was in this given state with a reward. Now we extend this provably safe reinforcement learning concept with the safety verification module that gets also states. It can be a subset of our states or a slightly different pre-processed set of states that contain the information that is safety relevant. And now we can close this loop in two different ways. One is we let the safety verification compute all safe actions, so we get a set of safe actions. And then the agent, the exploration process of it is actually constrained to the set so that only actions from the set are actually selected and executed. Yes?
So what do you mean by safe action? Do you have any particular threshold for the distance? Or how do you define the safety verification? Safety action?
So this basically, this safety verification box can be different methods. It can be a control barrier function that gives you an idea of like, for like one step, what are the actions that will keep you in the set. It can be also obtained from computing reachability analysis for the full set of actions. That's actually the first paper I will show you. And then kind of identifying which actions in this action space are safe and constraining the selection process to this.
Even the control barrier method, you should have that set defined. So you should have set that you want to be forward invariant, for example, right? So what is that set for you? What is the definition of the safety for you? That's
the safety definition in the end. I mean, it depends. So for reachability, so for the approaches I will show, it's basically avoiding unsafe areas or avoiding unsafe areas and complying to traffic rules. So that's the specification. And with that, we use the specification with, in my case, mainly set-based reachability analysis to obtain the safe actions that we then can use.
But given all the uncertainties about the motions of the other road users, how can you ensure safety?
Yeah, so this boils down to basically the models we're using for ourselves, but also for the other traffic participants. So for other traffic participants, we would use an over-approximative model that basically bounds is in the bounds of their acceleration. And then we can calculate their future occupancies. And then that is, for example, our unsafe set that we want to avoid. And we have usually some model of our own ecosystems, so the vehicle we want to control. And then we kind of perform reachability analysis for our ecosystem and see if we intersect with these unsafe areas that we computed for our traffic participants or static obstacles. Yeah.
So can you mind asking another question or?
Yeah. No.
So in the presence of some sort of uncertainty, like this Brown mentioned, the probability of reaching any set is 1 in long term. So it's kind of, or at least I think it's impossible to say you can't say if there is a guarantee that I don't reach a particular set. You can say that in a particular time I will not get there, or the probability is of getting into that set is small. But if you have this uncertainty, how can you guarantee that probability is 1?
Yeah, so we are assuming bounded uncertainty. These can be fairly large, but if we do, these methods, you get probabilistic guarantees once you consider probabilistic noise. In this case, we're assuming that we can actually bound the noise or bound the uncertainties in our system. And I don't think that's necessarily a wrong assumption because
no, but there is a probability involved. You should say the probability of reaching that set is 90%.
So these are worst case assumptions. So we are over approximating our dynamics of our own system and the environment. So we get the worst case dynamics. Okay. So action masking actually was used mainly for discrete action spaces so far. We recently wrote a paper on how to actually convey this to continuous spaces. I won't go into detail to this, but basically this is like one of the concepts. The second concept, how you can close the loop, is you let the agent select an action and only if it's unsafe, you correct it. And you can do this correction, or in the literature, it's done in 2 different ways. One is action replacement, where you just have, for example, a fail-safe controller, or you have some function that provides you a safe action in case you determine this action you're seeing right now from your agent is unsafe. The alternative is saying, oh, I want to minimally perturb the action that my agent proposed. And then what people usually do is they solve some kind of optimization problem to actually find the closest safe action. The first paper I will go into detail is actually an action projection approach, and the second is an action masking approach. What we did a survey on this whole concept of provably safe reinforcement learning, and what I, for example, found surprising by that is that actually action replacement is something that works very well, where you would think, oh, it's maybe better to only minimally interfere with the action. So if you're interested in like more conceptually analyzing these, then maybe that's something, or in the topic of provably safe reinforcement learning, maybe that's something you want to check out. Yeah.
So when you replace the action, are you changing the trajectory of the vehicle? Are you affecting the dynamic of the system? Is it possible that you create some sort of oscillation in the system?
Yeah, that can happen potentially. It's like that goes more into like how aligned is your safety and your performance objective. So your reward is to some extent usually a mixture of both. And like if this is fairly aligned. So for stabilization tasks, it's often the case that if you have a pendulum, your most performant action is stabilizing, and it's also the most safe action because you usually want to avoid to flip down. So then, yeah, it's kind of a good setup, but if that's not the case, then it can be challenging to define the safety verification in a way that it doesn't disrupt the learning process too much. But actually what we see, at least in some setups, is that the safety verification can also have the opposite effect and make learning feasible, because sometimes for high dimensional systems, it's very difficult for reinforcement learning to find a small part of the action space in a given state that actually is meaningful with respect to fulfilling the task. And we can use these methods also more in a guiding sense to really let the agent focus on the actions that are actually worth exploring. So my go-to example for this is for autonomous driving. What we saw a lot is if you just vanilla learn, then the first 100,000 training steps, the agent just learns to stay on the road. But we knew the road before, so we could kind of restrict the learning, or in particular the action space, already to the actions that we keep the agent on the road, and by that kind of remove this part in the beginning where we're basically learning something that we already know, because we usually have some form of representation of the road that we actually use in our learning process.
In your safety, is it, for example, collision is part of the safety in your case? Can it be part of the safety that the collision doesn't happen?
Yeah, so
if, for example, is it possible that the action is that going from 80 miles per hour to 20 miles per hour to avoid your collision? Is it possible that this happens?
So like the very first paper that I wrote was basically on highway driving with this concept. And there we're always had like to maintain a safe distance, in a sense that we never ended up in a state where if the vehicle in front of us suddenly started braking, we couldn't stop before it actually stopped. The only thing that you can't really circumvent is like if someone cuts into you, then you're trying to retain your safe distance as fast as possible. But if someone cuts in and then brakes, like full brakes, then you can. So in the end, what we need to restrict us to is, I guess, legal safety. So in any dynamic environment, we usually can't avoid collisions at all, because you can always have mad drivers, mad other robots around you that just have the only purpose to colliding with you. But you can kind of ensure that you're safe with respect to legal requirements. Okay. Yeah.
So folks, we're on slide 4 of 20. And these questions are great, but I think we're all keen to see what you've done.
Yeah.
And then pocket your questions, I think, and reflect on them, and hopefully we can have a good long discussion at the end too.
Yeah. Okay. So definitely focus on the most important part. So let's start with the first paper I wanted to introduce. As said, it's an action projection paper. And here, what we really wanted to look into, so we often have nonlinear models of our own agent, and these are already challenging for these formal methods, but they also are just like less conservative than linear over approximations. We also wanted to look at a environment where we have dynamic obstacles. So we need a prediction horizon to actually ensure that is larger than our actual planning execution, to ensure that we're not colliding, to basically see where these other obstacles might be in the future. And we wanted to have something that is actually not application specific, but where we can define this provably safe reinforcement learning with the minimal input that we thought we could make. So the idea here is we want to learn reach avoid tasks. So we want to reach a goal while avoiding collisions with dynamic and static obstacles. And we guard this with set-based reachability analysis. So here's again this action projection figure where the agent selects an action and then it's corrected. How do we do this? So this is our action space or our input space. for like in controls perspective. And then these red areas are our unsafe sets. These can be statics, but they can also be dynamic, meaning that for every time step, we have a different unsafe set. So like it would evolve over time for dynamic obstacles. And then this is our current state of our ecosystem. For simplicity, it's just one state, but we can also have a state set. So uncertainty in our own position. Now what we do is we compute our forward reachable set, which you can see here in gray. And we have our agent selective action that is now this action AT. Due to the way we select these forward reachable sets and we compute, So due to the way we select the set representation for our action space, but also for our reachability analysis, we can actually preserve a parameterization in our input space in these reachable sets, so that we in the end can actually kind of have these constraints, or like we basically get constraints on, I'm very sorry, but like my husband doesn't stop calling me for like a very long time. Is it fine if I don't know where my phone is, if I pick it up? Usually he stops eventually, but it's like for
Never had that happen. The dating time of these seminars, I think there's some conflicts. There might be some others that I'm not remembering, but if anybody has a conflict and you can't do this day and time and you really want to attend, let me know. For now, it looks all good though, so we won't change anything. Everything okay?
Yeah, everything okay, but I'm very sorry. Okay, so I was saying we compute these reachable sets and we parameterize these in a way that we basically get input or constraints on our input or action space. And we can leverage these constraints then in the end to formulate an optimization problem with which we can find the closest safe action within Euclidean distance now in this input set or action set. So we would then lastly use this action and then let this be executed by the environment. So this is the concept for the setup, and what we're assuming to be given is we have some system dynamics. So as said, these can be nonlinear dynamics. We have our unsafe sets as polytopes, and we represent our action set as zonotopes. And what we want to find is the safe actions with the minimal correction. Because maybe not everyone is familiar with zonotopes, I want to give you just a brief idea of what these are. So they are basically a convex set representation that are meaningful or like performant in at least some set operations. So they are defined by a center and these generators. And these alphas here are basically a scaling factor in front of these generators, and they are always bounded between -1 and 1. And this makes it actually very useful to use these generator space, or basically these alphas, directly for our learning approach. So in the end, we actually learn in this alpha generator space instead of our actual physical action space. So what we obtain is we have this problem where, just take one further, this alpha A is the action proposed by the agent, and this alpha is basically the closest safe action that we want to obtain. We use the Euclidean norm as distance metric, and then these constraints are actually constraints on this alpha, where they are kind of posed as being in polynomial level sets. So here, this is basically what we get when we're intersecting these polytopes with our polynomial zonotopes that come out of our reachability analysis with our zonotope as action space. So we can in the end then nicely formulate this as mixed and integer quadratic program and actually can solve this efficiently. So to give you an example, here we have a task where we have a drone that needs to track this dashed trajectory. So it's an infeasible trajectory because it's not allowed to go into this red area. So this is the unsafe static area. Yeah, so you cannot optimally track the trajectory without violating the safety constraints. We have a reward that basically is defined by the gym that we used here. So it's mainly optimality with respect to how far we are from our optimal trajectory and how much action we use. We measure our state with like position orientation and velocity, and also give the actions to our agent. And we use a very standard reinforcement learning algorithm, PPO, to as kind of the surrounding algorithm where we embed our safety verification. So we trained 3 different setups.
Quick clarifying question about the mathematical model. Is there an explicit uncertainty model, or rather the zonotopes could model bounded uncertainty, and exactly how the uncertainty evolves is buried underneath and could be many things?
Yeah, so basically this W here is the noise. That's some kind of set. So we define, I think here also zonotopes for that. So that's our bounded noise of our ecosystem. As said, we can also have noise in our initial state. So that X is also initially not a point, but a set. And then for these unsafe sets, I would say the noise is actually kind of hidden in the computed unsafe sets. So for, let's say, for a traffic participant, we can observe at least with some uncertainty their current state. And what we then do, we actually assume basically a point mass model to compute their reachable sets. But then we make them more realistic by constraining it A to the road, and then also B a priori constraining it to traffic rule compliance. So we would have basically removed the occupancy that would be the space that a following vehicle need to keep to a leading vehicle. So yeah, so there we're kind of making it less conservative. Once we, for example, detect that a vehicle is not keeping a safe distance to a leading vehicle, then we would kind of remove this constraint, and the prediction would grow. Yeah. I think another detail here is also we're doing this in a time discrete way, right? Because like in the end, every X time steps, the RL agent produces a signal, but our world doesn't evolve in a time discrete way. So we're in the end also always we're actually computing interval reachable sets. So and kind of encapsulate 2 reachable sets between 2 time points to basically consider that time evolves continuously. Okay, so for this first paper here, we have 3 different agents. The safe agent is what I just explained, so this action projection agent. We have one violation penalty agent that is a reinforcement learning agent that receives a penalty whenever it's getting into the unsafe area. And we have a baseline agent that is completely unaware of safety and just tracks the trajectory. What we observe is that for training, we see that our safe and baseline agents converge similarly fast. The violation penalty agent takes about 5 times longer to converge to a similarly high reward. So we have a better sample efficiency here. We also see that the action projection actually works, and we don't see any safety violations already during training when we have this safety verification. Now, if we look at the deployment result, what you can see here is the gray is the one that is unaware of any safety and just tracking the trajectory. This offset from the optimal one is mainly due to disturbances. And then the blue one is our violation penalty agent. So we still see at least some violations even after training, and we trained it for much longer, obviously. And our safe agent basically sticks in this white area and approximately tracks the trajectory. So I think I will skip this and rather show you this the video on driving, because we also had a driving example if in the end there's still time. And I want to give you a quick idea at least on what we did on action masking for ships. So here we are really looking into these traffic rules, because collision avoidance at sea is really structured by that. And the road, we have lanes, and these are mainly determining where our vehicles are in the future. But on the water, we don't have this, so it's these rules are very important for collision avoidance. However, they're a priori were specified in natural language, so not directly human, machine interpretable, and also to some extent ambiguous for formal methods. One nice feature of this application, though, is that it's actually the set of traffic rules is much more manageable than for driving. So I have a colleague in Munich, he's formalizing German traffic rules on highways and in urban settings in his PhD. And I think already for highways, we formalized like 30 traffic rules, and we actually only have 6 rules that we formalized then for this open sea situation. So the research question in this paper is, can we actually guarantee traffic rule compliance for a reinforcement learning agent, meaning that it's guaranteed to comply to these traffic rules? We look at an open sea situation with power-driven vessels, because this is A, the most common setup, but also B, limits our rule set significantly. We have 2 traffic participants. The main reason for that is that the rules are actually not provably safe for more than 2 as of now. So human captains can just find their way also with 3 vessels on the water, how to evade each other. But the formalization as it exists is not clear for more than 2 traffic participants. And for this initial work here, we also don't look into uncertainties. So our observations don't have noise as of now. So because maybe you're not familiar with the traffic rules on the water, here's a quick overview of what they are. So the main rules are these 3, and there are 2 types of vessels: giveway vessels, which have to evade, and stand-on vessels, which have to keep their course and speed. The crossing situation is a bit like right before left, head-on both evade to the right, and for overtaking, this giveway vessel here would sail much faster, and then can choose on which side it wants to overtake the stand-on vessel. However, if like any of these vessels in our situation don't stick to these traffic rules, then there's an additional rule which is very vaguely specified in this convention on the sea, so the COIREX, basically say even if you're a stand-on vessel and have to keep your course and speed, if there's an imminent risk of collision, you still need to evade and try to minimize at least the collision risk or also the impact. So this is very vague, and therefore we developed an emergency controller for this situation, because otherwise we couldn't kind of close our loop in this paper. But in general, this is something that is also not specified enough yet to really have one solution that is the correct solution. So how do we formalize these traffic rules? So let's have a look at this situation, this crossing situation. Now our eagle vessel is our giveway vessel, and then we have in gray our obstacle vessel. This is the formalization, and let's go through it step by step. So we have a globally operator around it, so this rule always has to hold, and then within we have an implication structure where if the left-hand side is true, then the right-hand side has to hold. And the left-hand side basically specifies that this crossing situation is persistent and existed for some time interval. And then if that's the case, so that's basically the leftmost figure, then the this ego vessel here now has to perform an evasive maneuver to the right. And this has to be in such a way that in a later time interval, we have like a predicate that determines if there's still a collision possibility between these two, and that has to be false for within a like later time interval. So in total, as said, we formalized these 6 rules. And now the question is, how do we integrate these rules in a safety verification process so that we can actually get all safe actions that lead to traffic rule compliant behavior. So for that, we're now living in a discrete action space. So we have a discrete set of actions that are a combination of different steering angles and accelerations. And we designed a state chart model to basically obtain this like the set of provably safe actions. So in the initial sum situation, you have your ego vessel, you have your obstacle vessel, and there's no conflict between both of them. So all our actions are safe, and therefore A phi is our full action space. Now let's look at this crossing situation. So we have an obstacle vessel coming from the right. We would predict the rule compliant behavior of this obstacle vessel, which is keeping its course and speed, and then testing different actions to identify or to verify which of them actually lead to a valid maneuver, but also B, within the time horizon, actually no collision possibility between the two vessels anymore. And then what we obtain is we obtain kind of a set of verified actions. And this is the set our reinforcement learning agent can then choose from. We have a very similar process also for the head-on and overtaking situation. If the ego vessel is a stand-on vessel, that's kind of a trivial case because there's only one safe action that is keeping the course and speed, so no course change and no acceleration. Also an example why pure learning is very difficult in this case, because it's very hard for the agent to actually converge to one single action, especially in a continuous space. Now, what if this obstacle vessel is actually the giveaway vessel but doesn't do its part? Then we would detect this by now a set-based reachability analysis for this obstacle vessel. So we over-approximate the future occupancy and see that would intersect with our plan. If that's the case, then we go from this normal operation into our emergency operation, where we have one specific emergency controller that then steers us actually to the rear end of our obstacle vessel to avoid the collision. Yeah. So this is the verification concept. Now let's have a quick look at the results. So I'm developing this framework called Common Ocean, and we are representing our traffic situations as Common Ocean scenario, where we have an obstacle vessel with a trajectory, and we have our ego vessel's initial state and goal state. We used handcrafted scenarios to make it very critical in the sense that we knew that the vessels are actually crossing each other's paths for training, but we also evaluated on real-world AIS data, so maritime traffic data. We have a reward that is, I would say, fairly standard and a state space or a state that lets the agent observe its own state and its surrounding, as well as the goal. And again, we used PPO as our reinforcement learning approach. So again, we trained 3 agents. The safe agent is our provably safe agent that has the safety verification module. The rule reward agent doesn't, like there you remove this verification module, But you still have a component in the reward that indicates approximately how well an action is with respect to the rules. And then lastly, we have a baseline agent that doesn't have this dense rule reward, but only is sparsely informed about collisions with as negative events towards safer behavior. So what we see in the end is that actually our safe and baseline agent reach similarly high goal reaching rates. The rule reward agent performs the best with respect to goal reaching, but the rule reward and the baseline agent both still have rule violations during training, and also in our test set, we frequently see them violating our formalized traffic rules, while our safe agent never even experiences them rule violations. So that validates our approach. So to conclude, we looked into how safety verification can actually lead to more efficient, so less samples, and hopefully also more effective. So at least not in the example that I showed necessarily, maybe a little bit quadrotor example, where we actually get an also performance gain from this guidance of the safety verification. We have I showed you an algorithm that actually works efficiently for dynamic environments, which is definitely challenging for safety guarantees. And we discussed a little bit how natural language specifications could be translated to temporal logic to make them computationally tractable and integratable into these approaches. And I want to end with basically, to some extent, my vision. So I believe that this combination of formal methods and machine learning could be actually a very fruitful combination to have more effective algorithms, but also more robust and more interpretable algorithms by using the knowledge we have about the world in a formalized way to guide the machine learning, especially in real-world applications where it might be difficult to obtain a large amount of data and we have to rely more on some model-based knowledge. So with that, thank you for your attention. I also want to thank my collaborators, and I'm happy to take your questions. Yeah.
I'm curious for the, when you're doing the policy gradient for PPO, how does that work with the for the projected actions in practice? Because like the probability of those actions is now like 0 once you apply that, right?
So the short answer is it depends. So for action masking, we can show that basically you can view it as a dropout layer at the end of your policy, like you have discrete actions, and that you don't really need to change your policy gradient. For action projection, there is an argument of including this, let's say, last computation step where you solve this optimization problem. I'm actually right now working on a paper with a colleague in Munich, Hanna. She is looking into these differentiable CVX pi layers and how to include this. What we actually see is that it's better to not, because they actually mess up the gradient information in a direction that is kind of relevant. So if you want to chat more about this, I'm happy to show you the results there. What we also, for the continuous action masking, which we just recently presented a paper, there, again, we think that it's a good idea because you basically get some information of how the action set looks in a specific state and give this to the agent. In our experiments, we just did some basic control examples. We didn't really see much of a difference. If we hyperparameter tune for both settings, it didn't really matter. So we're still looking into, is there really a benefit from this actual kind of implementation effort to integrate this in the backward pass as well? For replacement, there's an interesting paper by Hunt et al. That actually shows that you don't need to integrate it in the backward pass. So for action replacement, there's some theory why these two MDPs are equivalent. We also comment on that definitely in our survey paper, but I'm also happy to share this work with you. Yeah.
Yeah, I'm curious, it's easy to generate multiple vehicle time at the same time. They have maybe competing like intent mechanisms. Yeah.
You mean like in a multi-agent setting where you have like multiple agents? I mean, you could definitely use this also for multiple agents in one environment, but if you have means of communications, it probably also makes sense to also set it more up in like a multi-agent setup where you can basically maybe account for constraints or costs of different agents. What I think I would be excited about also with respect to this temporal logic is how can we still in like a single agent setting encode preferences or biases of humans better into like a specific controller. So like you could have a human stating, oh, I'm like I like reaching my goal fast. I don't care about comfort as like a specification. Like how can we integrate these preferences in our algorithms in a way that we still prioritize safety over preference? So yeah.
Can I ask a follow-up to that question? So have you considered a case where there's bilateral interactions between the ego vehicle and the dynamic obstacle? So specifically, from what I could tell, the unsafe set for the dynamic obstacle is independent of the actions of the ego vehicle. But if the dynamic obstacle is reacting to the ego vehicle such that the calculation of your safe action set depends on the trajectory of your actions, then this makes it a lot more complicated.
Yeah, I agree. So I think I mean, because we iteratively recompute the reachable set, so it's not there, and then we we definitely get some of the interactions, but we also encode this to some extent in a way how we make the sets less conservative, like keeping a safe distance to a leading vehicle. But yeah, we don't have a way that is it's much more indirect as of now. It would be better to have this more nuance. So right now we have, let's say, this like leading vehicle safe distance violation. If we see it, we remove this assumption that it's a good driver, and then it has like a larger occupancy. But there are much more nuances that we as humans detect from other drivers, right? Like it's often very small things, like how well is the road followed. So how can we integrate this better in maybe how over approximative we compute the reachable sets of the other drivers? So let's say, I think we do the same thing as humans, right? You're on the road, there's a driver that drives very smoothly. Your prediction of their reachable set is very tight. And if they suddenly do something weird, something happens in their car, like a spider drops down or something, like you're very surprised. Versus if you have a driver that is kind of already not really following the lanes, then you would already keep a larger safe distance. So how, like these intuitions we have, like how we interact with other people, how much do we want to integrate them in our safety verification tool? Like we can definitely reduce the bounds on like how over approximative a model is for a driver. But yeah, we would need to have like a semantic reasoning from our environment into our drivers, and then but I think we need to some extent do this to really have performant autonomous cars, because we don't want to be always considering the worst case.
Following up on that, do you have an idea of how suboptimal you are with respect to the optimal trajectory when you have the safety?
I mean, I know for this like very first work where we always like, I don't have a good number, but for this very first work I did on highway driving, we had a discrete action space where the agent could only stay on its lane or change its lane to left and right. And whenever we couldn't verify any of these actions, we switched to a proven adaptive cruise controller. And I think we switched to it for about 40% of the time. So that gives you maybe a rough idea of like what is there to optimize. So there's definitely room for that. And what we definitely saw in another paper on like urban driving is for intersection driving, if we don't consider right-of-way rules or stoplights and just always assume we wait and the others pass, then like our performance drops significantly. So we had, I think, like, now I'm really guessing, I don't know the exact numbers anymore, but I think we had like 60 or 70% goal reaching with like the baseline. But then if we had the safety shield, we had like 20 or 30, because we always stopped whenever there was a chance of someone else passing. So this also motivated to a large extent looking more into traffic rules and how to like more smoothly integrate them to have more performant or also more realistic solutions in the end. Yeah.
Okay, well, we're past
Yeah.
time. Let's, so now you've all met Dr. Krasowski, yes, you know what she's up to, and I'm sure she'd be delighted to speak with you if you have more questions and interactions. So let's give her a hand.